By the end of the next decade, human footsteps may finally press into the red dust of Mars. NASA says this isn't speculation. It's the plan. The world is celebrating, dreaming, imagining the triumph. But beneath that optimism lies a faint tremor, a quiet unease that only grows the closer we look. Because Mars is not just another destination. It is a cold, ancient tomb of a planet, one that never wanted life, never welcomed it, and never forgave the universe for abandoning it. But Mars has a flaw, a fatal flaw, a flaw woven so deeply into the bones of the planet that every attempt to settle it becomes a fight against something far older and far more unforgiving. If you like the content, leave a like and subscribe to the channel as today we travel into the mysterious worlds of Mars. Let us begin. It is entirely possible that someone watching this video might be among the first 1,000 humans to leave Earth with no intention of ever calling it home again. If you're not already training in a space program, you may want to get started, because the window of opportunity is narrowing. The first generation of Martian settlers may very well be people alive today: engineers, scientists, tradespeople, medical professionals, and yes, everyday adventurers. Imagine it, staring through a reinforced glass window, watching our pale blue dot shrink into a faint star behind you as the engines hum through your bones. Earth becoming nothing more than a small memory suspended in darkness. Everything you've ever known, everyone you've ever loved, fading behind you as Mars grows larger and redder in the viewport. But as that new world rises ahead, a question hangs in the air. What exactly will life be like on Mars? What conditions will you face? What dangers will stalk every step you take? What challenges will any would-be Martian colonizer have to confront in a world where nature itself is not merely indifferent, but actively hostile? Because Mars is not alive, it is a dead world, a planet where the weather can swallow entire continents, where temperatures swing violently in a single day, where water hides deep in frozen traps, and where the atmosphere barely exists at all. To tame that world, to survive it, humanity will need technology at the sharpest, bleeding edge of innovation. And even then, Mars will test every system, every settlement, and every human being who dares to call it home. That is why tonight, we're re-exploring the conditions future colonists will face, and the technologies NASA and other space agencies are developing to give human beings a fighting chance on the red planet. So settle in. This isn't a travel brochure. This is the brutally honest reality of what colonizing Mars will demand. Before you can colonize Mars, you first have to reach Mars, and the trip isn't a quick hop. Under the most optimal launch conditions, the journey takes roughly 3 months. That might not sound too bad, more like a long ocean voyage than a desperate push through interplanetary darkness. But there is a catch, a very big one. The moment your spacecraft leaves the comforting embrace of Earth's magnetic field, you enter a region of space that is effectively unshielded from solar wind and cosmic radiation. Earth's magnetic field normally absorbs or deflects this radiation, sparing life on the surface from constant bombardment. But once you're beyond that protection, it's like taking off armor in the middle of a battlefield. Prolonged radiation exposure can cause increased cancer risk, accelerated aging, DNA damage, vision problems, impaired cognitive function, and even symptoms similar to Alzheimer's before you even arrive on Mars. This isn't a theoretical risk. Astronauts on the International Space Station already experience increased radiation levels, and they are still protected by a portion of Earth's magnetic field. Deep space travel removes that shield entirely. Fortunately, engineers have ideas. Hydrogen-rich shielding is the most promising. Radiation is best blocked by materials rich in hydrogen. Water happens to be ideal. It is dense, hydrogen-rich, and plentiful enough that a spacecraft would already be carrying it. A ship could be designed with water tanks built into the walls, creating a natural radiation barrier surrounding the cabin. This simple design could substantially reduce the risk to astronauts. Another idea involves artificial magnetic fields. Theoretically, we could generate a magnetic bubble around the spacecraft using super powerful electromagnets. In practice, we need a compact reactor capable of pumping out unimaginable amounts of energy, something we can build safely yet. So for now, water shielding remains the most feasible option. And after 3 long months inside a reinforced metal shell, exposed to cosmic dangers, extreme confinement, and isolation, the ship finally descends toward the 4th planet from the Sun. You're about to touch down on Mars, and this is where things get both familiar and completely alien. For a planet so far from home, Mars shares some surprising similarities with Earth. The Martian day, known as a sol, is only 39 minutes longer than an Earth day. Its rotational tilt is nearly identical to our 23.5 degrees, giving it seasons that mirror our own: spring, summer, autumn, and winter. Even the polar ice caps look eerily Earth-like, shimmering white formations at the planet's north and south poles. On paper, Mars seems almost approachable, almost friendly, but that illusion doesn't last long. Temperatures swing wildly. At the winter poles, it can drop to 43 C. At the equator in summer, it can reach 35 C. And within a single day at the equator, the temperature at your feet might be 23 C while your head is freezing at 0 C. That is not a typo. The atmosphere is so thin that heat can stay near the surface. Warmth escapes instantly. It's a world where the sun can warm a rock, but the air above remains icy cold. Mars is a world of contradictions, a world that looks calm and still until you learn what lurks beneath the surface of its tranquility. The polar ice caps aren't just scenic features, they are seasonal machines. Every winter, the poles fall into continuous darkness. Temperatures plummet so deeply that the atmosphere itself freezes. Layers of CO2 ice condense onto the surface, slabs so thick that orbiters can track their growth from space. Then in spring, these dry ice layers sublimate back into the atmosphere, dramatically altering atmospheric pressure and wind patterns. This seasonal freeze-thaw cycle is destabilizing, powerful, and central to one of the most feared Martian phenomena: the planet-wide dust storms. If you glanced at Mars through orbital photos, you might assume it's a quiet world, calm, frozen, lifeless. But spend long enough on the surface and something begins to appear on the horizon, something towering and brown and slow-moving. A wall of dust, a storm. At first glance, it might seem like a desert storm back on Earth, unpleasant but manageable. But Mars does not do manageable. This storm is growing, and growing, and growing, until its churning dust expands to cover an entire region, then a continent, then eventually the entire planet. These planet-wide superstorms erupt roughly every 3 Martian years, about every 5.5 Earth years. They can last weeks, sometimes months, blotting out the sun and plunging the world into a choking twilight. This isn't dramatic exaggeration. This is documented reality. The worst part? We still don't fully understand why they happen. Mars used to have a thick atmosphere, warm, wet, and capable of supporting liquid water. But over billions of years, its atmosphere escaped into space. Now, Mars has less than 1 of Earth's atmospheric volume, and that thin air is why Mars gets dangerously cold and why heat escapes instantly. But dust behaves differently. Dust absorbs sunlight, dust radiates heat, dust stays suspended in the weak gravity for weeks or months. In small amounts, dust warms the atmosphere. In large amounts, it creates a runaway feedback loop. Sunlight heats airborne dust. Warm dust heats the air. Warm air rises. Wind rushes in. More dust is lifted, and the cycle accelerates into a storm. This continues until Mars is wrapped in a swirling, suffocating shroud. For humans, this is a nightmare scenario. For robots, it's even worse. Dust storms don't have hurricane-force winds. In fact, because the air is so thin, the wind would barely push against your suit. The danger isn't physical force. The danger is darkness. The storms blot out so much sunlight that solar-powered rovers, like the legendary Opportunity, can recharge their batteries. And without power, something far worse happens. The heaters shut off. On Mars, night temperatures can plunge to 75 C, even at the equator. A rover with no heat slowly freezes to death. Opportunity nearly died this way in 2007 when a massive storm plunged its power to critical levels. Mission engineers cut operations to bare minimum, allowing the rover to whisper home only every 3 days. It survived. Spirit did not. In 2010, a dust storm covered its panels in a thick layer of electrostatic dust, reducing power to fatal levels. Spirit fell silent and never woke again, and in 2018, Opportunity finally met the same fate during another planet-wide storm. The last message the rover sent home was heartbreaking. My battery is low and it's getting dark. These storms don't just kill robots. They threaten habitats, solar farms, communication systems, and human survival itself. And this is only the beginning. By now you can see that Mars is not simply another planet waiting patiently for human explorers. It is an adversary, an ancient, frozen, and indifferent world that will challenge every assumption we bring to it. The most dramatic expression of this hostility is found in the dust storms that periodically consume the entire planet. These are not storms in the earthly sense. They are atmospheric transformations, engines of chaos that alter temperature, reduce sunlight to almost nothing, and reshape the behavior of the Martian atmosphere from top to bottom. To understand how future colonists might one day survive on Mars, we first need to understand the true scale of these storms, because they reveal how unforgiving the planet really is. Most Martian storms begin innocently enough. They start as spirals of heated air called dust devils, tall, twisting columns of dust and sand created when sunlight warms the surface so quickly that air begins to rise in violent spirals. On Mars, these dust devils number in the thousands every spring and summer, and some can stretch more than 8 kilometers into the sky. They sweep across the landscape, leaving long dark streaks on the ground and injecting fine particles into the air. These events create a constant haze of dust that lingers in the thin atmosphere for weeks or even months. But dust devils are merely the spark. The real danger begins when Martian winds begin stirring the surface sands in a process known as saltation. Saltation is one of the strange, counterintuitive realities of Mars. On Earth, fine dust is easy to pick up, but on Mars, fine grains cling together stubbornly because of electrostatic forces. Larger grains actually move more easily, so when winds blow across the Martian surface, it is the medium-sized grains, tiny sand particles, that get lifted first. They skip and hop across the ground and then crash back down, knocking the finer dust loose. With Mars' low gravity and thin air, this dust remains suspended far longer than it ever would on Earth. As more dust rises into the air, the atmosphere begins to warm rapidly because dust absorbs sunlight far more efficiently than the thin Martian air. That trapped warmth causes large columns of air to rise, sucking in more wind, which lifts even more dust. In a matter of days, a small regional storm can grow into something dozens of times larger. Then these growing patches of atmospheric chaos begin to merge. One storm joins another, then another. And without warning, an entire hemisphere is swallowed beneath a rolling, turbulent blanket of dust and shadow. Eventually, the storm may expand across the entire planet, obscuring the surface from space and blotting out the sun until it becomes nothing more than a pale pinprick. These planet-wide storms are among the most dramatic and terrifying weather events anywhere in the solar system. They can last for weeks or months, plunging the planet into near darkness and crippling the technology that humans depend on to survive. The greatest threat these storms pose isn't the wind itself. The air is far too thin to create the destructive force we see in movies. Instead, the danger comes from darkness. Scientists measure atmospheric opacity using a value called AOD, or aerosol optical depth. On a normal day, Mars might register an AOD of around 0.5. Even a moderately dusty day rarely exceeds a value of 2. For comparison, the thick, choking smoke from a severe Earth wildfire might reach 7. But during the largest storms on Mars, AOD values can soar to 9, 10, or even 11. That level of opacity nearly eliminates sunlight entirely. Solar power becomes almost useless. For solar-powered rovers or habitats, this is catastrophic. No story illustrates this more clearly than the fate of NASA's Mars rovers. Opportunity, which set out on a mission designed to last only 90 days, survived for nearly 15 years. But even it couldn't escape the wrath of a global dust storm. When the storm of 2018 enveloped the planet, Opportunity's solar panels could no longer gather enough light to keep the rover warm at night. As the temperature dropped to lethal levels, its systems began to shut down. The last message Opportunity ever sent to Earth was interpreted by mission engineers as, "My battery is low and it's getting dark." After months of attempts to revive it, Opportunity was declared dead, its systems frozen by the cold, its panels buried under dust, its mission completed but cut short by the Martian environment. Even nuclear-powered rovers like Curiosity aren't immune. Though they can survive without sunlight, they rely on relay satellites orbiting Mars to communicate with Earth. During planet-wide storms, the atmosphere expands as the dust heats it, and satellite orbits become unstable. To avoid plummeting into the atmosphere, they must burn fuel for corrections, fuel they cannot replace. Meanwhile, signals from the surface become weaker, scattered by the turbulent air. Combined, these effects can isolate a rover or a colony, forcing them to endure weeks of silence. But the soil beneath the colonists' feet will be just as challenging as the storms above their heads. Martian regolith is a curious mixture of possibilities and dangers. It contains many of the nutrients plants need to grow, including phosphorus, potassium, and magnesium. In fact, experiments on Earth using Martian soil simulants have successfully grown tomatoes, quinoa, radishes, peas, leeks, and many other crops, often with yields nearly comparable to Earth-grown versions. But the soil is sterile. It has never been alive. It has no organic matter, no microbes, no natural fluffiness that allows roots to breathe and water to flow. To grow food on Mars, colonists will have to enrich the soil, adding organic matter, aerating it, and constantly managing its chemistry. Worse still is the presence of calcium perchlorate, a toxic salt that clings to Martian dust and infiltrates the soil almost everywhere on the planet. Perchlorates are dangerous to humans, causing thyroid problems and interfering with the blood's ability to transport oxygen. Plants absorb them readily, meaning crops grown directly in untreated Martian soil would be unsafe to eat. Yet these same perchlorates may also become essential to survival. They absorb water from the air helping extract liquid water in a place where humidity is low. And when heated, perchlorates release oxygen. So Martian soil contains the ingredients for both toxic exposure and life-saving resources, depending on how colonists manipulate it. Fortunately, perchlorates can be removed. One method is as simple as rinsing the soil repeatedly with water and then collecting and processing the runoff. Another solution is biological. Certain bacteria can consume perchlorates and release oxygen as a byproduct. Once the soil is cleaned and enriched, it becomes capable of supporting life, as long as plants grow inside pressurized, heated greenhouses that protect them from the cold, radiation, and storms outside. Growing food on Mars isn't just about survival. It is also about protecting the mental health of settlers. Fresh vegetables improve mood, boost immune function, and supply antioxidants that help mitigate radiation damage, something future settlers will desperately need. But while soil and storms shape life on the surface, exploration will depend on robotics. And Mars is pushing engineers to create machines that move, think, and survive in ways never needed on Earth. Ingenuity, the first helicopter to ever fly on another world, demonstrated that flight is possible even in an atmosphere so thin it is practically a vacuum. Designed to make only 5 flights, Ingenuity completed 72 over 3 years, scouting terrain, taking aerial photos, and proving that powered flight could revolutionize exploration. But flight is only one step. The future lies in robots that can walk, run, and think independently. That is why NASA is collaborating with Boston Dynamics to create robotic explorers inspired by Spot, the quadruped robot capable of navigating rubble, slopes, sand, and uneven terrain. Unlike rovers, Spot doesn't rely on slow, predetermined paths. It perceives the world through a network of cameras and sensors, constructs real-time 3D maps, and makes autonomous decisions about where to go and how to get there. It reacts instantly to obstacles, stabilizes itself when it slips, and can even operate in complete darkness. For Mars, that level of autonomy is crucial. Communication delays of 3 to 22 minutes make remote piloting impossible. A robot must think for itself. This autonomy becomes especially important for exploring caves and lava tubes, underground worlds where ancient water might have flowed and where signs of past life could be hiding. More importantly, these caves may someday shelter human colonies, shielding them from radiation and storms. But caves block radio signals, making traditional rovers useless inside. Spot-like robots, guided by advanced AIs such as Nebula, can enter these caves, map their interiors, navigate blindly around obstacles, and relay their discoveries once they return to the surface. NASA envisions swarms of these robots exploring together, communicating with one another, sharing tasks, and collectively mapping environments no human has ever seen. This robotic groundwork will pave the way for the first permanent human settlements. Colonists won't arrive on a raw, untouched Mars. They will land at sites prepared long in advance by machinery, habitats partially assembled, landing pads softened and cleared, and resource extraction equipment already running. But robots can do everything. Colonists will still have to navigate storms, manage energy systems, maintain greenhouses, and make decisions without immediate help from Earth. And with communication delays, every emergency will require local solutions. On Mars, there is no calling home for quick advice. Every colonist must be engineer, scientist, mechanic, and survival expert at once. Despite these immense challenges, and because of them, Mars continues to draw us in. It is not simply a world of danger, it is a world of opportunity, of mystery, of possible futures. The people who first set foot on Mars will face a level of adversity no previous generation has ever known. And yet, decades of research, exploration, and innovation have shown that everything standing between humanity and the red planet can be overcome. Storms can be endured, soil can be purified, water can be extracted, oxygen can be generated, food can be grown, exploration can be automated, and with enough patience and courage, human presence on Mars can shift from impossible dream to inevitable milestone. As the first wave of colonists touches down on the Martian surface, their mission begins long before they take a single step outside. Before any human can breathe Martian air, albeit filtered, pressurized, and sterilized robotic precursors will have spent months or years preparing the ground, testing the soil, surveying landing zones, and building the foundation of a future settlement. On Earth, building a home is a logistical challenge. On Mars, it is a monumental undertaking. Everything colonists need, the shelter, water processing units, energy systems, scientific equipment, life support infrastructure, must be delivered or constructed in advance. No single spacecraft can carry it all. Instead, a fleet of autonomous landers and robotic crews arrives first, tasked with sculpting a strip of this alien world into the beginnings of a livable outpost. And the choice of location is one of the most consequential decisions in the entire mission. At present, several regions of Mars stand out as potentially viable settlement sites. The polar regions, for instance, offer vast supplies of water ice, essential not only for drinking, but also for agriculture, oxygen production, and the manufacture of rocket fuel. But the poles are intensely cold, plunged into months of darkness during winter, and battered by storms that stretch across the horizon. Another location that has captured scientific attention is the Korolev crater, an immense 81-kilometer-wide bowl filled with a massive year-round deposit of water ice. This frozen reservoir could support a settlement for decades, but it sits in a region where sunlight is weak and temperatures are severe. Colonists might survive there, but it would be a harsh, energy-hungry environment. More promising, especially for long-term, scalable habitats, are mid-latitude regions where permafrost lies beneath the surface. These areas allow easier extraction of water while offering much milder temperatures than the poles. Combined with their lower elevation, especially in the northern hemisphere, these regions provide thicker atmospheric pressure, a small but meaningful buffer against radiation, and a significant advantage during landing. Even a thin improvement in air density can make entry, descent, and landing safer for large spacecraft. And then there are the lava tubes and natural caves, ancient geological formations created by flowing magma that collapsed long ago, leaving behind tunnels that may stretch for kilometers. These underground chambers are among the most tantalizing locations on Mars because they may offer natural roofs that protect colonists from cosmic radiation and meteorite impacts, as well as temperatures that remain relatively stable year-round. Scientists have already identified numerous cave entrances from orbit, some of which may be large enough to house entire buildings. But to use them, we need detailed maps, something only robotic explorers can provide. Once a suitable location is chosen, construction begins. The most realistic designs for Martian habitats rely heavily on 3D printing technology. The idea is elegant: use the planet's own regolith as a building material. Specialized robots would scoop the soil, mix it with water ice, and process it into a concrete-like slurry. Then, layer by layer, the habitat walls would be printed into a shell capable of withstanding the internal pressure needed to support human breathing. These printed shells would then be covered with additional regolith, either dumped by robots or blown into place to create a thick shield against cosmic radiation. Mars lacks a global magnetic field, so without this literal mountain of dirt above them, colonists would absorb a lifetime's radiation in only a few years. The solutions may be technologically advanced, but the principle is simple. The planet itself must become the colonists' armor. Once the printed structures are complete, the colonists begin the long task of activating every system. They connect power lines, install air recyclers, integrate water purification units, and check every seal, valve, and panel. Even with robots handling the heaviest tasks, the work is painstaking. Until the habitats are fully ready, the new arrivals will likely live in inflatable modules, or the spacecraft they came in small, cramped temporary shelters that offer survival but little comfort. These first nights may be the most psychologically intense of the entire mission. Unfamiliar gravity, endless darkness, a silent world stretching for thousands of kilometers in every direction, and the awareness that Earth is now a distant light in the sky. Once the colony is sealed, pressurized and stabilized, the atmosphere inside must be created. One method relies on electrolysis, splitting water into hydrogen and oxygen. The oxygen becomes breathable air, while the hydrogen can be converted into rocket fuel or used in industrial processes. Another method extracts oxygen directly from Mars' CO2-rich atmosphere. NASA is already testing this technology with the MOXIE experiment aboard the Perseverance rover, which has successfully generated small amounts of oxygen. In a full-scale habitat, much larger versions of this system would run continuously, replenishing breathable air and storing excess oxygen in tanks as backup. All of these systems require energy. Solar panels are the most straightforward power source, but Mars receives only about 40 of the sunlight Earth does, meaning panels must be far larger to generate the same output. Even then, dust storms, especially global ones, can plunge power production dangerously close to zero. For this reason, nuclear reactors are widely considered essential for long-term survival. A compact, low-temperature fission reactor could provide continuous power regardless of sunlight or weather, allowing habitats to run heaters, lights, oxygen generators, and water processors without interruption. Ideally, a combination of nuclear, solar, and battery storage systems will ensure redundancy. On Mars, energy is not a convenience, it is a matter of life or death. Water, too, is non-negotiable. Colonists will likely melt subsurface ice or dig into permafrost layers, heating the soil and capturing the resulting vapor before filtering it. Water recycling will be mandatory. On the International Space Station, up to 90% of water is reclaimed from humidity, breath, sweat, and even urine. Martian colonies may need to exceed that efficiency. Once extracted, water can then be used for drinking, irrigation, electrolysis, and sanitation. And like oxygen, water must be stored in tanks that can survive the cold nights without freezing solid. When all these systems are combined, air, water, heat, radiation shielding, and power, a Martian habitat becomes a small bubble of Earth, carved into an environment that otherwise does not care if human beings live or die. Inside this bubble, colonists will grow food, maintain equipment, sleep, work, and experience every emotional high and low that comes with living in such a confined, remote place. Growing plants, especially fresh fruits and vegetables, will be essential not only for nutrition, but for mental health. Studies already show that astronauts on long-duration missions experience psychological benefits from tending to plants. On Mars, with its isolation, confinement, and constant background danger, this connection to something living will matter even more. Yet even with food, water, and air, the psychological challenges of Martian life may prove harder than any engineering problem. The settlers will live in small groups, likely fewer than a dozen people, trapped inside limited space for months or years at a time. They will eat similar meals repeatedly, follow strict routines, and face daily maintenance tasks essential to survival. Outside their habitats lies not a welcoming world, but a barren, silent desert where temperatures can swing more than 100 degrees between day and night. There will be moments of awe, but there will also be moments of overwhelming isolation. On Earth, remote stations in Antarctica or on submarines already require regular psychological screening, yet even those environments offer the comfort of knowing that evacuation is possible. On Mars, evacuation is not an option. The settlers must endure, adapt, and support one another through every crisis, every storm, every failure. Physically, Mars also inflicts its own toll. After the Kelly twin study, where astronaut Scott Kelly spent a year on the ISS, NASA learned that long-term exposure to low gravity causes muscle atrophy, bone density loss, cardiovascular strain, changes in vision, immune system suppression, and even alterations in DNA expression. Martian gravity is only 38 that of Earth. That means every colonist will need to exercise extensively, every day, to maintain health. Treadmills, resistance machines, and stationary bikes will become as essential as oxygen. Over time, humans born on Mars might evolve or be genetically engineered to withstand radiation better, metabolize nutrients differently, or function normally in lower gravity. Some scientists argue that such enhancements are inevitable, but whether accepted or resisted, the fact remains: living on Mars will change us, and not all changes will be predictable. Despite the physical risks, the psychological strain, the environmental hostility, and the countless unknowns, there is no shortage of volunteers. Every time a space agency or private company mentions the possibility of a crewed Mars mission, thousands of hopeful applicants raise their hands. Some see adventure, some see meaning, some see destiny. Others simply feel the pull of that red world, an urge that has existed in human imagination for generations. Building a colony on Mars will test our technology, endurance, and unity as a species. But the fact that so many people are willing to go, knowing the dangers, reveals something profound about humanity. We are explorers by nature. We are driven by curiosity. We are compelled to step into the unknown, even when the unknown might destroy us. Mars is not a place that welcomes life, but it is a place that challenges it. And perhaps that challenge is exactly why we are drawn there. Even after the habitats are built, the systems activated, and the colony begins to breathe its first artificial breaths, the greatest challenge still lies ahead: the simple act of continuing. On Mars, survival is not a milestone. It is a daily negotiation. The colonists must monitor every gauge, every valve, every panel of solar cells, every circuit in the life support system. A minor leak in the habitat S-pressure shell could become fatal in minutes. A glitch in the oxygen recyclers could suffocate an entire crew. A damaged heater could freeze pipes and rupture water systems overnight. There is no redundancy in numbers, no dozen other settlements nearby to send help, no emergency rescue team waiting on standby. Every problem must be solved by the people who are already there with whatever tools they have before the problem becomes too large to reverse. On Mars, maintenance is not a chore, it is a survival ritual. Communication with Earth, too, will always be tinged with loneliness. Depending on the positions of the planets, a single transmission may require anywhere from 3 to 22 minutes to arrive. A colonist who sends an urgent question must wait nearly an hour for a full back-and-forth reply. Real-time conversations are impossible. A cry for immediate help, if the situation could even allow such a thing, would echo into a void of delay. So messages become more like letters than conversations, moments of connection stretched across the vast, silent ocean of space. birthdays will be celebrated 20 minutes late. News from home will arrive in fragments. And while colonists will maintain emotional ties to Earth, an unavoidable truth will settle into their minds over time. They are not just far away, they are effectively alone. And yet, within that isolation, a new kind of society will begin to form. Humans have lived in remote environments before, on Arctic research stations, aboard submarines, in high-altitude observatories, and even in sealed habitats designed to simulate Mars. Every one of those environments reveals a common truth. Small groups of people, when bound by necessity, develop their own rhythms, traditions, and ways of coping. Martian settlers will do the same. They may create rituals around mealtime or exercise breaks, hold weekly meetings to discuss emotional well-being, or develop communal routines to break the monotony of life inside the habitat. Psychological support plans will be integrated into daily life, not as an afterthought, but as a critical component of survival, equal in importance to food and oxygen. The settlers must become not just a crew, but a family one that depends on every member to function. Over time, they will venture farther outside the habitat. What begins as short extravehicular excursions, carefully timed walks to inspect equipment or gather samples, will expand into longer journeys using pressurized rovers. These vehicles will allow colonists to explore nearby valleys, cliffs, ancient riverbeds, and craters. Each trip will provide vital data about the environment and likely reveal new challenges, from unexpectedly soft terrain to dust buildup that threatens machinery. Some expeditions will be breathtaking, others will be nerve-wracking, but every trip will remind the settlers of the immense alien world beyond their walls, a planet that is quiet, beautiful, and utterly indifferent to them. As the colony stabilizes, more missions will follow. The second wave will bring more people, more equipment, more advanced reactors, larger greenhouses, and perhaps the first modular expansion units that allow habitats to grow beyond their original footprint. What was once a single outpost might become a cluster connected by tunnels, heating lines, and communication cables, forming a small but growing settlement. Each new arrival will reduce isolation, broaden the skill pool, and add redundancy to critical tasks. Slowly, the colony will shift from simply surviving to planning for the future. Children may one day be born on Mars, though not until medical science has developed a deeper understanding of how low gravity affects early development. Entire fields of research will emerge: Martian agriculture, Martian geology, Martian biology, Martian medicine. The planet itself will shape the culture of those who live there. The settlers will be pioneers not only in location, but in identity. Yet for all the progress, Mars will continue to fight back. Dust storms will still roll across the horizon, darkening the sky for weeks and forcing colonists to rely on stored power and nuclear energy. Machinery will still age and break down. Solar panels will still accumulate dust. Radiation will still pose long-term health risks. And gravity, just 38 of Earth-S, will still tug on their bones and muscles in unfamiliar, subtle, and possibly harmful ways. Daily exercise routines will remain mandatory. Medical facilities will need to evolve. Future settlers might require genetic protections, hormone treatments, or specialized therapies to counteract the physical toll of living on another planet. Every generation born or raised on Mars will adapt a little more to this alien environment. They may grow taller, or develop denser bones, or alter the balance of their inner ear to adapt to the lower gravity. Humanity will remain human, but perhaps in a slightly new form. Despite all of these risks, the will to explore persists. The same force that drove ancient navigators across uncharted oceans now drives engineers, scientists, pilots, and adventurous souls across the void of space. For some, the call of Mars is irresistible. It is the lure of a new frontier, the chance to write the next chapter of human history, the opportunity to become part of a story that will be told for centuries. Mars is not comfortable, safe, or forgiving, but it is profoundly meaningful. Standing on the surface of a new world changes a person. The skies are unfamiliar, the landscape silent, the colors muted. And yet, in that stillness, the planet seems to whisper something ancient, something that reminds humans that we are not meant to stay in one place forever. So the question becomes, will mankind truly establish a permanent colony on Mars? With NASA targeting the late 2030s for the first crewed landing, the prospect is no longer a distant fantasy. It is a rapidly approaching reality. Private space companies are designing spacecraft capable of carrying dozens of passengers. Nations are discussing long-term settlement architectures. Universities are training the scientists and engineers who will one day build Martian infrastructure. The groundwork is being laid, step by step, test by test, mission by mission. And although obstacles remain technological, psychological, ethical, and financial, the momentum behind Mars exploration has never been stronger. And what about you? After traveling through the dangers, challenges, and wonders of the Red Planet, after imagining the storms, the soil, the solitude, the technology, and the sheer perseverance required, how tempted are you to become one of those early colonizers? Have the realities of Martian life driven you away from the idea, or stirred something inside you? Are you frightened by the thought of stepping onto a world that has killed every robot we've ever sent? Or are you excited by the chance to rise to the challenge, to carve out a foothold in the face of great odds, to stand on a world that has never known human footprints, never heard human voices, never seen human light? This could happen within our lifetimes. You or people you know could conceivably be among the very first to ever live on another planet. Imagine what it would mean to wake up beneath an alien sky, to walk across a landscape untouched for billions of years, to see two moons drifting overhead, to watch a sunrise tinted by dust and thin air, to know that you are part of humanity's greatest leap. It is a daunting thought and an exhilarating one, and perhaps tucked somewhere in your mind, there is a small spark, a part of you that whispers, maybe. A part that wonders what life would feel like on a world so quiet, so ancient, so far from home. A part that thrills at the idea of humanity stepping beyond Earth as cradle at last. And if that spark exists in you at all, if the idea of Mars stirs even a faint sense of temptation, then that says everything you need to know about who we are as a species. We are curious, we are restless, we are builders, explorers, dreamers. And even when faced with a dusty, storm-covered planet that seems determined to resist us, we find a way to reach out, step into the unknown, and claim our place among the stars.